Buosa, are you here? Buosa, can you share your screen? All right. Good. We can see a screen. Thank you. All right. This is a magnetic one. All right. Let me see who else. We still have a few slides of presentation to confirm, but since it's already 1 o'clock, so why don't we begin with the first presentation? Huayin, can you share your screen?
Yeah, sure.
Yeah,
I just see Alexander is here. Oh, Xiaolu Zhu is joining.
Yes, I saw it. So we don't have time to confirm the share screen. So let's start from the first one, please.
Xiaolu.
Huayin?
Yeah, well, Xiaolu is here. Xiaolu, can you share your screen?
All right.
Oh, okay, I'll share instead.
Good afternoon, everybody. Today I will talk about the topic with the title Detecting Heavy Metal Ions with Ultra-Low Concentrations based on composite material incorporating reduced graphene oxide and sodium arsenate. The heavy metal pollution is one of the most serious environmental problems. The reduced graphene RGO is sensitive to some external substance and can be used to detect heavy metal ions. However, the amount of oxygen-containing functional groups contained in RGO is often not enough to meet the demand of ultra-low concentration detection. To alleviate this problem, we propose a new method that uses composite material incorporating reduced graphene oxide and sodium arsenate. Here is the materials and method. This figure shows the setup in our experiment. Here is the electrochemical workstation. It's an instrument. Here is the apparatus that includes gold microelectrode array and the connecting device. Here is the enlarged figure of the microelectrode array. On the right side, here's the pictures for our prepared test materials and the solutions for the heavy metal ions. The below figure shows the enlarged image of the microelectrode array. The gel graphene composite is formed here. Next, we define the sensitivity of this system using this equation. There are 4 different types of configurations. That means we use different materials. The first is RGO, then is SA, RGO and SA, and RGO, SA, and calcium ion. Here there are 2 tables. The first table is the sensitive, the calculated sensitivity of each detection material. Here it's not covered with gold film. We can see that with different test materials, calculated sensitivity is different. And the second table shows the sensitivity of each detection material covered with gold film. On the chip covered with the thin gold film, the current value of RV curves is higher than that without gold film. And the detection sensitivity for the copper and the lead is improved. Here is the systematic results in our experiment. Left side, this figure shows the void ampere characteristics of heavy metal ions detected in this system through composite material. The applied voltage is 1 volt. On the right side, there are the experimental results for different configurations of composite materials. That means, for example, the first group is DR water. The second configuration is RGO. The third configuration is SA. The fourth configuration is SA plus RGO. So the first figure is for copper ion detection. The second figure is for the lead ion detection. The third figure is for the palladium ion detection. From these figures, we can conclude that the SA graphene composite material can be used to detect these 3 types of heavy metal ions with ultra-low concentrations. We can see that the lowest concentration can be reached 1 picomole. and their different concentration can be distinguished. The second is the conductance changes among different configurations for detecting the palladium are most obvious under the conditions of 1 picomole and 1 millimole. So here is the summary. Thanks for your attention. Good afternoon.
All right. Just to clarify, we have 5 or 6 minutes for the poster talk, correct?
We should have 3 minutes actually. And if you have any questions, you can just use the chat, and you can also send emails to the presenters. And we all have the email information in your agenda.
That's right. All right. Thank you for explanation, Huaying. So our next one is from Hamid. Hamid, are you here? If not, we'll just play the video from Huaying's side. I don't think so. So Huaying, you can play number 2, the electronic structure and optical properties of cubic and orthorhombic perovskite understanding from DFT. Yep, please. Thank you.
How are you? I am Hamid Mansour Ghaitan. I am a PhD candidate at King's University. Today I will present my work, electronic structure and optical properties of inorganic cesium-lead X-ray in 2 phases, cubic and orthorhombic. I will use a DFT calculation in my work. And as we know, cesium-lead halide can be used for solar cells and line emitting diode devices. In this work, we will use the Vinto-K code, and we can select 6 methods: LDE, PBE, EV, PBE, SOL, MBG, new MBG, and unmodified MBG, GGA. These methods are very important. We don't know which one give a band gap or optical properties comparable to experiments. Our purpose is to check which one is the best to give us a comparable result to the experimental one. We found after we calculated the structural and optical properties that the cubic and orthorhombic has direct energy band gap. And also, the most important, the band gap computed with in BGGA potential were found in a good agreement with experimental result, as we can see later. And also, optical properties of this halide almost give similar optical properties, and a wide temperature range of operation for cesium chloride. You can see here our method. We used density functional theory DFT, but we selected the Vinto-K package because there are many codes. For structural properties, we used PBE GGA, and for electronic and optical properties, we selected these 6 methods. The structural properties, our results show that this column represents the cubic cesium chloride, iodide, chloride, bromide. This one cesium iodide, cesium bromide, cesium chloride, cubic, in cubic phase. We can see a gradual shift of the peaks to the right when we replace iodide with bromide and chloride. Also the same for orthorhombic, the iodide, bromide, and chloride. For electronic properties, as you can see, we use the 6 method from LDE, PBE, PG, and modified MG, MBG, and new MBG. For cubic cesium bromide as an example, we selected cesium bromide here as an example. This represents the cubic one, and this one represents the orthorhombic one for cesium bromide. How can we know the value of energy band gap for everyone? We draw this figure, which represent or show us the clear view of the energy band gap for this method. This LDA x-axis represent the DFT method, and y-axis represent energy band gap. As we can see for MBG and experimental are in a good agreement. As you can see, this one for cesium iodide, bromide, and chloride. These are represent the experiment. To understand band gap more better, we want to see which atom contribute to the energy band gap. This one, the left graph, represents a total and partial density of state for cesium lead iodide in cubic phase. As we can see, cesium does not contribute to energy band gap, as you can see, but lead and the bromide contribute almost. Also for orthorhombic cesium lead bromide, cesium does not contribute to energy band gap. For optical properties, we just selected absorption coefficient and refraction. As we can see, for cesium chloride, shift to cesium iodide, and also for refraction, shifted from down for cesium iodide to bromide. The dot lines are for orthorhombic, and solid lines represent the cubic phase. All this work was almost done before, but with addition to spin orbital coupling, because we have a heavy lead element, and spin orbital coupling is very important to be used to study energy band gap. But in this work, we did not mention because we have not space to mention. Thank you so much.
All right, number 2. Number 3, we'll have our first live talk from Weiheng Xu, Bioinspired Composite Fibers as Versatile Sensors. So Weiheng, you can share your screen and start talking. All right, let me unmute you. I'm not sure if you are unmuted. Okay, you are unmuted now. Thank you.
Hello, can you hear me?
Yes, clearly. Thank you.
Okay. Hello, my name is Weiheng Xu, and today I will be talking about bio-inspired composite fibers as versatile sensors. So there are basically 2 types of VOC sensors. First is solid state sensors, which are usually composed of a semiconducting material. And on the right are some selected solid state VOC sensors. You can see they all have very low limit of detection, and they have high selectivity. They are mostly used for biological applications, but the downside is their manufacturability and their cost, as well as they often require a high working temperature. The second type is polymer-based nanocomposite, which usually composed of a polymer matrix plus conducting nanoparticles. The benefit of this type is they are easy for fabrication, their cost is low, they're highly flexible, they have high chemical stability, but the downside is their low sensitivity. As you can see, the limit of detection usually are in the 100 or 1,000 parts per million. So in this work, we draw inspiration from a vascular plant as how they efficiently transport water vapor through vertical transpiration channels as well as horizontal diffusion pits. So we 3D printed a triaxial spinneret, and then we injected different channels with different polymer. So on the outer side is a mechanically strong TPU with no pores, and in the middle is a TPU plus multi-wall copper nanotube and graphene nanoplatelet as the chemi-resistive layer, and the inner layer is a porous TPU for gas diffusion. And through using solvent-induced phase separation, we generated a continuous hollow core for gas transportation. So we optimized the middle layer by percolation threshold, rheology behavior, mechanical behavior, and chemi-resistive behavior. And by constructing the fiber in this 4-layer structure, we were able to obtain higher response, better stability, and their humidity and temperature. And here is our device, where the middle part is the multi-layer fiber. We inject different types of VOC gases through the sensor, and we obtain the resistivity change. And you can see the limit of detection is to down to 15 parts per million for xylene. And also this the multi-layer structure, especially the outer pore-free TPU, enabled stable mechanical behavior under different strain, and also the fiber was able to detect vibration motion at 0.1% strain, as well as pressure sensing, which could all be used for future inline VOC sensor devices. Thank you very much.
Right. Thank you, Wilhelm. So if you have questions, make sure you email him. Number 4, I think the author is Federico. He also uploaded the video. Huayin, I think you can share your screen. The title is New Class of Cross-Linking Free Nanofiber Biomaterials from Hydra Nematocyst Proteins.
Nematocysts are harpoon-like organelles possessing remarkable mechanical properties. Recently, 2 novel protein components building up the nematocyst.
Can you start from the beginning, Brian?
Nematocysts are harpoon-like organelles possessing remarkable mechanical properties. Recently, 2 novel protein components building up the nematocyst capsule wall in Hydra were identified. The first one is the Cnidarian proline-rich protein 1, CPP1, characterized by a rigid polyproline motif flanked by 2 cysteine-rich domains, comprising 6 cysteine residues in a conserved pattern. The second one is the elastic cnidoine, possessing an elastic silk-like domain flanked by several CRDs. Thanks to the presence of these short CRDs, CPP1 and cnidoine spontaneously cross-link via the sulfide bonds. The combination of rigid CPP1 and elastic cnidoine therefore seems to be a very promising strategy for the design of new biomaterials that are capable of forming stable structures by a spontaneous cross-linking. These biomaterials could be suitable in the area of cell and tissue culture because of their low cytotoxicity. We started by comparing the elastic modulus of isolated nematocysts with spontaneously cross-linked bulk proteins. These charged nematocysts and recombinant CPP1 and cnidoine expressed in E. coli were subjected to AFM measurements in phosphate buffer. The mean and the standard deviation of effective elastic moduli of the capsule was 2 megapascal, whereas the elastic moduli of CPP1 and cnidoine blocks were 7.8 and 2.3 megapascal respectively. Note that the validation of the obtained elastic moduli is not easy because there has been no report on the mechanical properties of either nematocyst capsules or its protein constituents. The obtained results suggest that the bulk cnidine protein is softer than the bulk CPP1, which can be attributed to the disorder's silk-like motif. For the fabrication of uniform protein nanofibers by electrospinning, the preparative conditions were systematically optimized. Interestingly, both fibers type remained stable even after rigorous washing and immersion into bulk water, owing to the simultaneous cross-linking of cysteine-rich domains. This makes our nanofibers clearly different from other protein nanofibers that are not stable without chemical cross-linkers. Following the quantitative assessment of mechanical properties, the potential of cnidine and CPP1 nanofibers is examined towards the maintenance of human mesenchymal stem cells. Since about 95% of cells exhibited the immunoreactivity to a stem cell marker, anti-STRO1, after 20 days of culture, recombinant CPP1 and recombinant cnidine nanofibers have a potential as a new biocompatible material inspired by the tough and elastic hydronematocyst structure.
All right.
Bone-like organelles possessing.
I think it was stuck, Huaying. Is it over?
Yeah, this one's
Okay.
over.
All right. Thank you. Number 5. Let me see. Xviewer, are you here? No. All right, Huaying, you can play number 5 video.
Sure.
Thanks.
Xavier Cassel, and I will speak about my work on carbon monopole antenna fabrication and characterization at microwaves. This work has been carried out in the multifunctional materials team at the Institute of Electronic and Digital Technologies, University of Rennes in France. The use of carbon fiber tissue as a replacement for a metal radiating element is investigated here to fabricate microwave antennas embedded into composite material panels. A full composite losange monopole antenna is studied here because this design is easy to fabricate and to characterize. The radiating element is a single square embedded into an E-glass fiber polyester laminate. This sample is placed on a round plane and fed at the corner through a SMA connector. Moreover, the size of the sample gives the operating frequency of the antenna at microwaves. A full composite antenna and a reference counterpart made from a plain copper sheet are therefore investigated. First of all, the carbon fiber tissue was characterized through a 4-probe setup. As expected, the sheet resistance of the carbon fiber tissue is larger than that of the copper sheet, but its value remains satisfactory in view of microwave applications. Electrical conductivity of both samples was computed from the formula here, rating the sheet resistance, the conductivity, and the sheet thickness. It is worth noting that the ohmic resistance of the radiating element is equal to the sheet resistance of the tissue due to its square shape. The dielectric characteristics, namely the relative permittivity and the loss tangent of the E-glass fiber polyester laminate, were performed by the stop perturbation technique. The relative permittivity is equal to 4.5 and the loss tangent equal to 0.01 at 1 GHz. The two planar losange monopole antennas, carbon fiber and copper counterparts, were fabricated by the infusion process. First, the radiating elements were cut to the required size. Second, 4 plies of E-glass fiber tissue were placed on the both sides of the radiating element. Third, the set was infused under vacuum with the liquid polyester resin on a glass slab. The polymerization reaction was complete after 4 hours at room temperatures, and the samples were suitable for release without any additional post-bake. Microwave performance of the full composite antenna and of the copper counterpart was performed through gain measurement in an anechoic chamber. Below 2.1 GHz, the measured gain of both antennas are strictly alike, demonstrating the relevance of the carbon fiber tissue used as radiating element. Between 2.1 GHz up to 4.5 GHz, a difference in gain value close to 1 dB is observed. At higher frequencies, the carbon fiber tissue becomes lothy and the difference in gain values is larger from 2 dB up to 5 dB. In closing, I would like to thank very sincerely our financial supports and you for your kind attention.
All right, very nice talk about antenna. Number 6, Daewon Lee, are you here? I don't think so. I didn't see the name. Number 7, Yeching Wang, are you here? No. Number 8, Bashir Morshed, I think you prefer playing the pre-recorded video. Is that correct? Okay, let's play the video again. Huaying. It's number 8.
Yeah. Number
The
8.
model is inkjet printed multi-layer thin film flexible electronics fabrication of conductive, resistive, and dielectric electric polymers.
Hello, everyone. Welcome to the poster monolithic inkjet printed multi-layer thin flexible electronics fabrication of conductive, resistive, and dielectric polymers. My name is Bashir Morshad. I am associate professor in the Department of Computer Science, Texas Tech University. My collaborators are Tomoko Fujiwara, Frank Andrasik, and Robert Hewitt from University of Memphis. In this NSF-funded project, we are developing a thin film inkjet printed fabrication process. Thin film inkjet printed process is a new additive fabrication process that makes it possible to produce flexible electronics in a very, very low cost for a large area, and which is not possible in traditional electronic microfabrication electronics. This thin film layer is very controllable. That's why we can have precise control over conductivity, and also we can develop multi-layer 3D structures with this type of flexible electronics. We have been exploring this technique for some time, and we have fabricated many types of sensors, electrodes, and experimented with various electronic components that includes resistor capacitors and different type of dielectric materials. We are using Dematic's material deposition printer for this purpose, which has a 10 picoliter drop size of 16 MEMS-based nozzle with 20 micrometer pitch. We are using silver nanoparticle ink. We have achieved 25 milliohms per square surface resistivity on polyamide. The thickness of these are 1.8 micrometer. We also fabricated other types of sensors and electrodes, like, for example, ECG electrodes, and respiration sensors, multi-layer capacitors, etc. Figure 1 shows the printer and the printing process. Figure 2 shows some characteristics of the inks that is used, that includes contact angle and surface roughness. The surface roughness is captured by AFM microscope. Also, in the figure 3, you can see some experimental data of the thin films, showing the AFM on the left side of figure 3, that the thickness is 1.8 micrometer. And it also shows my multi-layer sensor fabrication technique on the right side. Figure 4 shows some of the sensors that we have developed and some data that we collected with this, showing the functionality and feasibility of this. Overall, this technique of monolithic multi-layer fabrication process can provide next generation flexible electronics using various basic electronic circuit development process. So thank you everyone for attending this poster session.
All right, thank you, Bashir. Very nice talk about inkjet printing. Number 9, we have Monish. Are you here? All right, fine. We are going to play the video again.
Sure.
The topic is magnetic higher dispersive Fresnel ions with controllable foci and dual images. Thank you.
I think Nagi Bosa is here.
Oh, Bosa here. Nagi, are you here?
Oh wait, I need to unmute him. Wait a minute.
Okay, Nagi, do you want to present? Do you prefer the video? Let me unmute Nagi. Oh. Yeah, I couldn't see him either probably because he didn't change the name. Maybe you can type. Do you want to? Okay.
Yes. Okay. Now I can. Thank you. So it was unmute. Thank you so much. Okay.
You prefer presenting on your side?
Yeah. Okay.
That's good. Thank you.
Thank you. Okay. Okay. Thank you, everybody, to join for my poster under the title "A Magnetic Chiral Dispersive Vernal Lens with Controllable Foci and Dual Images." So my name is Naji Bouausa, and with the other author, Prof. Monish Chatterjee. So we are from the Department of Electrical and Computer Engineering, University of Dayton. So when we speak about as the research group, we are working the chiral material. So we assume the chiral material to be the second medium. So we can see here like it's become dependent for epsilon 2, mu 2, and the kappa, which this is the third part. This is the kappa that we apply for the chiral material. Since we are speaking about the chiral material, that means that the normal constitutive relation will be modified. So if we make the kappa is equal 0 here, so it's back to the normal constitutive relation. And one of the behavior of the chiral material that when there is incident wave, we assuming that is polarized incident field. So that's mean there is two reflected field and two transmitted field, but those field, it have the behavior of the circulation, left circular polarization, right circular polarization, and also we know to that like the chiral material has 4 chiral wave number. So there's 2 backward and 2 forward and 2 backward. So I am working in the 2 forward. This is the equation for the incident incident and reflected and transmitted field. Since we have 2 for reflected, so there's 2, 1 RCB, LCB for the same for the transmitted field. And now, since we have that's mean is also like the Snell's law, it's not become normal Snell's law. We have like the new Snell's law, which we call it Snell's law under chilarity. So if we make that kappa is equal 0, it will be back to the Snell's law, to the normal Snell's law. Also, we have like the theta T1, theta T2, where that the transmitted angle, and for sure MB1 and MB2 is the phase index. And we assuming that we have 2 cases like loss or with dielectric loss. So that's mean like epsilon R2, like the permeability for the chiral material will be complex. And this is like denser to rare case. So we study many cases. This is one of those cases. And you can see here that we have the anomalous Proster angle. And by changing the kappa value, we can see that the right circular polarization is shifting to the reflection coefficient 1 or right is shifting to the right. However, the LCB is shifting in the left. And we have here like double inflection, which we assuming those is double TIR, which we approved that it will be also anomalous. This is by changing the chiral material itself, like we change mu R2, that's mean we change the magnetic material for the second medium. And we make the kappa 0. Now we make them, so in that case, we study some application, one of them the slab and the thin film. Now we are coming to study the magnetic dispersive chiral Fresnel lens with controllable foci. So that's mean we have to control in that we make the magnetic Fresnel cell itself is to be chirality. So those the equation for the Fresnel lens, and we study now we apply like the incident angle to study the behavior for the incident angle for the Fresnel lens, and we make the control the focal length is constant. So we can see here by make the kappa is equal 0, both RCB and LCB it was identical, but by changing the kappa value, we find like we have different incident angle for the RCB polarization and for LCB. Now we make the kappa, we change the kappa value, and we see that by changing the kappa, the incident angle itself to get 300 millimeter focal length, by changing the kappa value, there change in the value for the incident angle for RCB and LCB. And I would like to thank you. So in the poster, you can find all the cases that I studied, I show some of my results. Thank you so much.
All right. Thank you, Nagi. Very nice talk. We have number 10, Wojin Koi. Are you here? Wojin Koi? No. Korea. I'm pretty sure it's too early in Korea. we have the slides and we don't have the uploaded video. Is that correct, Huayin?
Yeah, yes, we just have the slide.
So maybe we can skip this one because it's not a video.
I'm checking if there is any sound in this slide.
Or maybe can you check this quickly, Huayin? Can you open it and see if there
No, I just opened it. No, there's no sound. I think we can just skip this one.
All right, thank you for the confirmation. We'll go to number 11, Manda. I'm sorry, I'm not sure if this is the right way to pronounce your name. Are you here? Number 11, Manda, the title is Efficient Green Mirrorless Leader from a Conjugated Polymer, PFO, co-PPV, MEHB in solution, copolymer solution behavior. Are you here? Okay, I didn't see the uploaded video. Did you see the Huayin? Number 11.
No, we didn't receive that.
All right, thank you. Let's just skip this one too. And we'll go to number 12, Ratiba. Are you here? Ratiba, I think Ratiba is here, and you are unmuted. Okay, Ratiba, do you prefer the recorded video of presenting by yourself?
Hello, everybody. You can put the video if you want.
All right, so we'll play the video again.
Yeah, I can put the PPT file if you want also, with the sun.
Well, if you want to present, just present on site.
I will try.
All right, let's see how it goes.
Okay.
Oh, so should I play it?
Maybe I have problem here. I can't exchange. Maybe it's you can put the video. I can't exchange my file.
Right.
Yeah, I'm sorry. I'm sorry.
Okay, okay. Let me share.
The video.
Okay, so let's start it.
This poster concerns biosourced composites for anechoic chamber absorber. This work is collaboration between ATR Lab and CEA. In anechoic chambers, the microwave absorber usually used are made from polymer matrix such as polyurethane impregnated in carbon solution. These absorbers show some limitations such as a loss of absorbing load and are also produced by petrochemical industry, which is a pollutant industry. Different absorbers based on natural material have been proposed in the literature, which show a willingness to provide environmentally friendly absorbing material, but with a low absorption performance today. Here we propose an absorber based on cork loaded with carbon particle. The cork presents several advantages. It is ecological, lightweight material. It is also a waterproof and fire resistant material, which make this material as good candidate to replace the polymer foam matrix in absorber materials. Here are presented photos of cork granules before and after carbon coating. The cork presents closed pores, so the load is retained by the open pores located only on the surface of the cork granule, as we can see here on this optical image. Here are photos of sample elaborated with different amount of carbon. The dielectric characterization of the sample show that the dielectric properties of composite increases with carbon amount, and we can note that we obtain a low permittivity associated with high dielectric losses, which is ideal for absorbing application. The measured dielectric properties were used to simulate the absorption performance of pyramidal absorber. This is the chosen geometry for the simulation, and the results show a reflection coefficient lower than -20 dB for practically all the composition. Here, same result is obtained for composition L4 and L5, and so the composition L4 is with a less carbon load was chosen for the prototype achievement. A pyramidal absorber prototype was then realized with this composition and with the 64 pyramids. This prototype has a similar dimension than the commercial absorber shown here in this photo. Here is the measurement of our prototype compared to its simulation, and we can observe a good concordance here between this result. Now, the measurement of this prototype is compared to commercial one for normal and oblique incidence of electromagnetic waves. We can see here that we obtain a better performance for our prototype than the commercial one, especially at low frequencies. The improvement is up to 27 dB. Simulation and measurement of the absorber temperature under electromagnetic wave incidence were also done. Here the measurement is done in GTM cell under power density of 53 watt per meter square. And this result shows that the temperature of our cork-based prototype increases more slowly than that of PU foam-based commercial absorber, which predict a better power resistance for our absorber. Thank you for your attention. This poster concerns.
All right. Thank you, Ratiba. I have a quick question. I messaged it in the chat window. Maybe you can find it later. So let me go to level 13. Is Masih Mr. Tobias here? So I think he's here. Let me unmute him.
Yes, hello.
Hi, you want to present on your slide, or you prefer the recorded video?
I would prefer to play the video if it would be possible, please.
All right, level 13. Huayin, can you play?
Yeah, sure.
Okay, thank you.
Okay, go ahead.
Hello everyone, my name is Maciej Tobis. I'm from Poland University of Technology, and I would like to present carbon RS2 composite, an attractive electrode material and electrochemical capacitors. Rhenium disulfide is a class of transition metal dichalcogenides, which is most commonly exploited in metal-ion batteries, but the application of capacitor is very lightly described. To this we have prepared various RS2 carbon composites, for example carbon nanotubes, three-dimensional graphenes, or graphene nanophotolytes by hydrothermal reaction, and use them as an electrodes and electrochemical capacitors. Here you can see the comparison of electrochemical performances for each of this material, and it occurs that the best performance was recorded for the rhenium disulfide deposited on the nanotubes. Here specifically you can see that not only the capacitance was improved, but also the charge propagation properties. Later we have decided to increase the operational voltage of this material, starting from the 0.5 volt, with the use of 1 millivolts per second. And it occurs that it was possible only to extend the operational voltage up to 0.8 volt. This effect is related to the catalytic activity of the RS2 structure, which is also increased by the use of nanotubes. Later we have decided to compare the effect of scan rate and application of different current densities for the composite material and for the raw materials. And as you can see, that not only the capacitance was improved, but also the RS2 deposited on the nanotubes exhibited significantly better charge propagation for about 40%. We have proved that we have obtained the demanded structure by the XRD, and also the nitrogen sorption-disruption proved that the textual properties of this material is very comparable to the materials. Later we have decided to compare this material in different electrolytes, and it occurs that the best performance was reached for the 1 molar lithium sulfate. Here you can see that not only the capacitance was improved, but also the energetic efficiency for this material was improved for about 30%. SEM and ADES images shows that the layers of RS2 is homogeneously distributed on the surface of the nanotubes. And just to summarize this work, we have prepared several carbon Arris-2 materials, and it occurs that the best performance was reached for the rhenium disulfide deposited on the nanotubes. Sadly, the catalytic effect of the Arris-2 structure caused limitation of the capacitor operating voltage up to 0.8 volt. I would like to also acknowledge the National Science Center of Poland for the financial support. Thank you for your attention.
All right, thank you, Mr. Tobias. Also very good talk on the EC capacitor work. And the number 14 for next. And see, we do not have an uploaded video. The author is Alex. Are you here? Let me check. No, I don't think Alex is here. Why can you confirm that there's no uploaded video for slide?
Wait, I think Alex is here. Wait.
Oh, I see. I'm sorry, Alex. I'm now on mute. I'm now unmuting you. Can you talk, Alex?
Hello.
Hey, Alex. How's it going?
I'm going right, but I am other Alex.
Oh, you are other Alex.
Alex Korolev, not Dmitriev. So
yeah, all right. Okay.
My turn over 5 other
so
speakers. So we don't have him here, but
yeah,
I am here. Let's wait.
Thank you, Alex.
Sorry. Okay. Dimitri, I think that's the other, the Alex for 14. So Huang, we don't have a recorded video, correct?
Let me see. 14. We have 14. Yeah.
We do?
We do not have 14. We have 50. Sorry.
Oh, okay. Yeah, that's what I thought. All right. Number 15. Ekaterina. Let me check it. The lady here. Do you see her, Ryan? I don't think I saw.
No.
All right, then we will play the video. Okay, the topic is effects of reinforcement on 3D printed polymer-derived silicon oxide combine.
Hello, today I will be presenting on the effects of reinforcements on 3D printed polymer-derived silicon oxycarbide. The motivation for this work is to use 3D printing to enable cost-efficient production of ceramics. Ceramics offer desirable material properties that cannot be achieved by metals or polymers. However, there are challenges to manufacturing of ceramic parts. Bulk ceramics cannot be cast or molded like metals and are hard to machine, therefore strongly limiting the part geometries that can be made. Therefore, this is a perfect space for additive manufacturing to change the game. Our team at HRL Laboratories is developing UV functional pre-ceramic polymers for use in conventional UV-based 3D printers. We've functionalized silicon-based pre-ceramic polymers with a UV functional group that facilitates cross-linking to create a polymer part that is pyrolyzed to yield a ceramic. In order to increase the toughness of our 3D printed ceramics, we can employ toughening mechanisms. The use of secondary phase reinforcements is a well-studied mechanism to increase the fracture toughness of ceramics. The two mechanisms that we're studying is particle reinforcement and whisker reinforcements. To quantify toughening of our ceramic, we used single-edge notched bend tests. As you can see from the K1C versus volume percent reinforcements plot, our neat, unreinforced 3D printed silicon oxycarbide material is right around 1 MPa root meter. With the addition of mullite particles, we can see that the toughness increases to 3.5 MPa root meter at 10 volume percent particle loading. With the addition of 8 volume percent silicon carbide whiskers, the fracture toughness increases to 4.5 MPa root meter. These values are close to toughness values seen in technical ceramics such as silicon carbide and alumina. In conclusion, we've demonstrated 3D printing of reinforced ceramics from UV functional pre-ceramic polymers. Particle and whisker reinforcements improve toughness of silicon oxycarbide from 1 MPa root meter in neat silicon oxycarbide to 3.5 and 4.5 MPa root meter for 10% molite and 8% silicon carbide whisker, respectively. And the toughness values that we see are on par with that of technical ceramics. Thank you for listening, and for more detailed information on methods and this work, please see the references cited below or contact me at my email listed above. Thank you.
Okay, very nice work on 3D printed polymer-derived ceramics. We have 16 for the number 16 for the next Rajesh. Let me check if Rajesh is here. No. So we all. I don't see the recorded video either. Huaying, can you confirm on your side?
Yeah, we do not have any material on this one.
Okay, so we'll skip that. Maybe good. Thank you, work. And next we have Ratiba on the glass foam composite for high power microwave absorption. And we have the recorded video, but I think Ratiba is also here too. So let me check. Yeah, Ratiba, I'm going to ask to unmute you. Do you prefer talking on your side or playing the video?
Playing the video, please, if it's possible.
All right.
Thank you.
Fine. Yep.
Thank you.
Yeah,
Thank you.
sure.
This poster concerns glass foam composite for high power microwave absorption. The aim of this work is to evaluate the performance of an inorganic matrix for microwave absorbing application. Thus, inorganic matrix present a good chemical resistance and high temperature stability. They are also eco-designed here because they are elaborated from recycled waste glass of 30. For the foam glass elaboration, the glass waste is first mixed with the foaming agent. This mixture is then heated following a three-step process: the temperature ramp, followed by operatic temperature step. In this step, the glass becomes viscous and the foaming agent reacts with the glass waste to produce gas bubble. The expansion and the cooling paths lead to the glass foam production. Different amounts of carbon are here used, between 0.5 and 5%. This curve and these photos show that when the amount of carbon increases, the foaming of the mixture increases and the density of the foam decreases. The limit is reached with 5% of carbon, for which the structure of the foam is altered. For the dielectric properties, we can note that very high values of dielectric losses are obtained for the samples and are associated to relatively low permittivity. However, the dielectric properties vary according to the percentage of carbon, but not in linear way. Here I present the dielectric properties of samples as function of the weight percentage of carbon, and we can observe that the permittivity decreases as a function of the carbon amount and increases for the higher percentage, and inversely for the dielectric losses. Maximum dielectric losses are obtained here for the glass foam made with 1.5% of carbon. Here are presented the dielectric properties of the same samples as a function of the foam densities. The real permittivity presents a linear evolution as function of the density independently of the carbon percentage, but the losses increases with density before decreasing for the last sample. This result confirms that the dielectric losses are a compromise between introduced carbon in the mixture and the unreacted carbon remaining in the final foam sample, but also to the density of the sample, which is monitored also by the carbon percentage. The chosen composition for the prototype was 1.5% of carbon percentage. Here I show an example of application of these absorbers. It consists on cost-effective high-power microwave termination to protect emitting systems from return signals. The simulation of absorption performance of this load shows that the wave is absorbed before reaching the bottom of the geometry, which confirms the good absorption performance of our material. Moreover, a good fit is obtained between a simulation and measurement of the reflection loss of this absorber. The power simulation of this load shows that the maximum of reached temperature under 73 kilowatt per meter square is around 400 degrees. The measurements show that for the same power density, no modification in the material behavior. So this material can be used as high power microwave terminations. Moreover, to improve the compromise density and dielectric properties, a combination of foaming agent can be used in order to reduce the density while keeping electromagnetic absorption. Here are presented photos of sample made the first with only carbon and for the second with a mixture of foaming agent. This last sample presents a very low permittivity while maintaining high level of losses, which induces a high absorption performance. This allows obtaining the best compromise between mass and shielding efficiency. Thank you for your attention.
Okay, thank you, Ratiba. I noticed that you gave a talk earlier about absorbance too. Very good talk. Thank you very much. Next we have number 18 from Milmia. I'm not sure, Zorica Milmia. I'm not sure if person's here. No. Huayin, can you also check if the slides have recorded audios inserted?
Sure. I think there is.
Okay, number 18.
Just share this one. Share my screen.
Hello, my name is Nikolina Nikolic and I'm from Vinča Institute of Nuclear Science from Belgrade, Serbia. I will shortly present our recent work of hydrogel nanocomposite photoactuator for direct optical to mechanical energy conversion obtained by ionizing irradiation. Photoactuators are class of smart materials that can produce irreversible mechanical deformation under light stimuli. Such materials attract tremendous interest due to their potential application in soft robotics, artificial muscles, and smart devices. Currently, the fabrication of photoactuators is mainly based on photothermal actuation mechanisms, which include expansion or contraction molecule, sorption or desorption, and phase transition. Thermosensitive hydrogel with gold nanoparticles are probably the most commonly used active layers that absorb light energy and convert it to thermal energy, causing irreversible mechanical deformation such as bending, curling, and spiraling. In this work, hydrogel nanocomposite photoactuator based on gold nanoparticles and polyanisopropyl acrylamide were synthesized by gamma irradiation. Two different shapes of gold nanoparticles were incorporated into cross-linked polymer matrix, and obtained hydrogel nanocomposites show typical absorption spectra with the 1 and the 2 characteristics absorption bands for gold nanospheres and nanorods. SEM and TEM analysis confirmed the formation of gold nanospheres with a diameter around 20 nanometers and gold nanorods with aspect ratio about 5. Thermoresponsive polymers have a critical phase transition temperature and show a significant change in volume with a small temperature change. Below this temperature they swell, but above this temperature they shrink. The obtained results show that the volume phase transition temperature of photoactuators can be adjusted by incorporation of different shapes of gold nanoparticles. It has been observed that the VPTT increased from gold nanospheres to gold nanorods. Moreover, we tested the photothermal shrinking under visible light irradiation. We used the lamp and laser, and it was observed a more pronounced photothermal effect in case of nanorods. Under laser radiation example with nanorods, the conversion of optical to mechanical energy is confirmed by clearly visible bending of hydrogel nanocomposite. We also investigate the electrical properties of hydrogel nanocomposites. It was shown that the electrical conductivity increased with increasing of temperature due to the smaller interparticle distance in collapsed state of nanocomposites. At the end, I would like to conclude that such a type of materials, thermoresponsive hydrogel nanocomposite device with wireless remote actuation and electrical control, has great potential for light harvesting and mechanical motion, which is required for the construction of soft smart actuator system for application in soft robotics, for dense information storage and efficient energy conversion. Thank you for your interest in our research.
Right. Thanks for the hydrogel nanocomposite presentation. Our number 19 talk is from Alexandra Korolev. I don't think he's here, so let's play the video, please, Huayin.
Can you hear me? Hello.
Yeah, I can hear you.
I am ready.
Yeah, it's your turn.
Chat. I try to play. Can you play my video, please?
Okay, sure.
Colleagues. Dear colleagues, our greetings from South Ural, Russia's Federal Center of Metallurgy and Machinery. We are glad to present the results of composite deformability modeling. It's a complex conclusion of several works for elasticity and deformability modeling, so the presentation concludes classification of layer models and examples of their testing and application. Regulation and prediction of composites deformability, elastic and plastic properties is the important problem in providing calculated limits of structures deformations under mechanical and thermomechanical load. What technological problems are cleared? The materials industry has to achieve up level of properties regulation. Not only regulation of mechanical properties, but regulation of deformability. Elastic and plastic properties. It could make structures design much more effective and accurate. Producing control of composite deformability can be useful and realized only in case of three factors according: effective deformability coding by parameters of composites' real behavior under different loads, simple and available methods of deformation modulus testing, most of them are hard and long-term, accurate methods of technological composite mix design and regulation to achieve design parameters. The presented classifications and related methods make the attempt to suggest principles of these problem solving, especially mix design for deformability regulation. The analysis of most composite deformability research shows that many years the composite deformability is correlated with mechanical properties, strength and density, but not with deformability of components. This method is too old. Practice has proven that materials with equal strength have different elasticity. For making the last, it's necessary to go on supramolecular or mesostructure scale of modeling. Summarizing past and current research, the following principles in the formation of elastic properties of composites can be highlighted. The first, composite is a three-phase structure, basic elements of which are binding matrix, aggregate, and the contact area between them, or interfacial transition zone ITZ. These components have different elasticity, and their different elasticity determines the overall deformation properties of the composite. Second, the contact area ITZ realizes surface energy, so ITZ deformability is mostly higher than other composite elements. ITZ is the basic element of viscoelasticity. Third, the stress-strain state of the composite does not under the principle of additivity. And fourth, the most popular are spherolytic composite structure models, but severed layers cross-sections are more applicated to models of elasticity calculation. Thus, the main aim of this research is to prove the applicability of the layer models and composite models of elasticity prediction. As the objects of research, polymer and cement composites were used. The following tasks were solved. composite deformability analysis, and layer elasticity calculation model proposal, different deformation model type application testing. Basic compositions for elasticity research were heavyweight and lightweight concretes and cured epoxy resin. These compositions were chosen because of their principal structural and deformability difference. To determine the fact concrete elasticity modules in our experiment, we used local producers' materials with definite elasticity modules and presentation. The contents of various classes mixture components are presented in following tables. In research, different methods of elasticity modules testing were used for cement and polymer composites. Standard methods of Russian state standards were used for concrete modules of elasticity determination. The elasticity modulus has been determined as a relation of 30% cracking stress to the sum of elastic relative deformation except plastic on stages delay by standard. For polymer samples, the bending test of elasticity modulus was used. 3-point bending tests of polymer samples were carried out on a continuous Olsen testing machine in a specially made small-sized chamber which provides heating. The examples of short-term elastic and plastic deformation testing under compression and bending are shown on presentation. Polymer composites have definitely elastic properties in normal conditions, but with heating, polymer structure becomes viscoelastic. The slight deformation surfaces are appearing. Polymer structure can be presented as a domains or macromolecules severed by ITZ. It can be noticed that there are traditional viscoelastic characters of concrete stress-strain conditions, but it's necessary to pay attention to plastic deformation of different concrete type. The heavyweight concrete with high elasticity modulus had less plastic deformations than usual, and lightweight concrete has in fact no significant plastic under compression. So the main factor of composite viscoelastic properties is the volume and elasticity level of ITZ. In heavyweight concrete, ITZ has the lowest density and elasticity, so the ITZ volume decreasing makes composite elasticity increase. In lightweight concrete, ITZ has the high density and plastic is minimal due to that. So by these examples, we can notice three types of structures. Mostly plastic is polymers under heating, mostly elastic is lightweight concretes and lightweight aggregates, and viscoelastic as heavyweight concretes. On the base of composites, deformability specifies the layer deformation models of different structure types are suggested. The matrix layers, depending on composite type, can be the ITZ only with mostly plastic properties, type PL, the binder only with mostly elastic properties, type EL, the binder and ITZ with viscoelastic properties, type EPL. Developing a calculation model of the composite deformative properties, the dependence of the elastic modulus on the layer model with the number of layers n, the elastic modulus of each layer and the related thickness of the layer was proposed. Further, the testing of layer modulus applications are presented. Here is presented the calculation layer PL model. The viscoelasticity is modeled as a packs of elastic polymer sheets stretched under load, with low rigid bonds between them. Here is presented layer model with entropy factor for elasticity models under definite temperature. Final equations were received for epoxy filled by a micromarble and others. Table presents the correlation of entropy layer PL model, calculated and the actual result differs not more than 15%. Here is presented the calculation EL model as a pack of elastic layers where ITZ is accepted because of its properties are equal to binder. According to the proposed calculation model, the light concrete elastic modulus equation includes factors of aggregates and binders elasticity models and related thicknesses. Their calculation algorithms are suggested too. In compositions of light concrete mixes of our own concrete mixing plant of demanded classes were used for testing. Table shows the calculation and testing result of the elastic modulus of light concretes. Calculated and actual result differs not more than 10%. Here is presented the calculation EPL model as a pack of elastic aggregate and binder layers divided by weakened ITZ layers. Also, we suggested algorithms of related thicknesses and modulus of elasticity by layer model determination. Working compositions of commercial concrete mixes of our concrete mixing plant were used for testing. The elastic modulus of the contact zone was determined by correlation method. Calculated and actual results starting from class B20 differs not more than 15%. The application of layer modules and composite elasticity prediction were suggested and proved. The modeling is based on classic composite structure elements such as matrix and aggregate. The matrix except binder includes contact zone ITZ, where adsorptive bonds dominate. Composite deformability research confirms that ITZ is the main factor of plastic deformations of composites. Thus, the deformation modeling principles were formulated on presentation. Using basic equation of elasticity modules depending on deformation properties of components, the methods of elasticity properties calculation for all kinds of layer modules were proposed and proved. It's made the base of composites with definite elasticity mixed composition design development. PL module is useful for viscoelastic or plastic deformation of composites when ITZ plays a matrix role. EL module is useful for composites with ITZ properties near or equal to binder properties. EPL module is useful for complex composites with weakened ITZ.
All right.
Sorry, it was the long version of presentation, but because I am the one who is not asleep in Russia, maybe you forgive me for this long time. Thank you.
All right. Thank you, Alexander. Very nice talk, very detailed. Our next talk is number 20. Let me see. Light-induced changes in the electronic structure of the metal molecular junctions. A computational modeling of real and design molecules. I didn't see the author here. All right, I think I see the author.
I'll stop the share.
Okay, thank you very much.
Hello and thank you. I will share my presentation now.
Okay, thank you. Olga and Veled Slave?
Yes.
Sorry. Okay, good.
Yes.
Thank you.
Yeah.
Can you see it?
Yes, we can see it.
All right.
Great.
Okay, thank you. All right. The title of the talk is Light-Induced Changes in the Electronic Structure of the Metal Molecule Junctions. And this is a purely computational approach. And we are from the Leibniz Institute of Polymer Research in Dresden, Germany. Here you see the working horse of our study. Our molecule is based on azobenzene. You can see this part here. Azobenzene exists in trans state, and this is planar state. And under UV illumination, it goes to cis state, which is bent. And during this light-induced changes, so we can basically control many things. But what is the most important for us is what related to organic electronics and to organic junctions. Here you see one example of our molecule, which is basically in contact with gold electrode. Which molecules are the objects of our study? As I already mentioned, one part is light responsive. This is called azobenzene. The next part is BTIFN, and the last one is spacer, which connects our molecules to the electrode. And here we distinguish between two molecules. This one is known from experiment. This one is designed, and the difference between them is basically in the order of different blocks, counting from the anchoring surface. And of course, we model trans and cis isomers, but not the transition between them under light illumination. What is also important that we try to reproduce this CAFM experiment. In which way? So remember, our molecule is attached, is fixed by this group to the surface of electrode, and the rest of the molecule is mobile. And here we put the gold tip, which is modeled as gold cluster consisting of 10 atoms. And our main research method is DFT calculation, which is performed in this commercial software. Here you see some details of our simulations. And we model, once again, cis and trans isomers for 2 molecules which are in contact with gold tip. This tip is, so to say, frozen, and the rest of the molecule, the organic part of the molecule, is mobile. For a designed molecule, for cis isomer, we'll also distinguish between different positions of gold tip, which is in contact with our molecule, and finally results. What is important that from experiment, it was shown that depending on the trans and cis isomerization state of the molecule, we basically have off state, which is trans, and on state, which is cis. And we try to explain why it happens for trans and cis isomerization. And here you see partially the answer. The delocalization of the electron on LUMO and HOMO orbitals is basically located exclusively on gold tips for trans isomers and includes the part of organic molecules in case of cis. This is, let's say, the proof why cis state is on and trans state is off. Trans state is acting as insulator. So again, for HOMO-LUMO orbitals, here you see the HOMO-LUMO orbitals as a function of the position of golden tip, and here we also can distinguish between some situation when we do not have any delocalization of HOMO and LUMO between the golden tip and the organic molecule, and partial delocalization, like in this case. We also can speculate which part of the molecule is the most conductive actor in this on and off switch. Here's some data for analysis, which again shows that for trans isomers, for experimental molecule and for designed molecule, this excess charge, let's say the charge transfer between the golden tip and the organic part of the molecule, is almost 0, whereas for cis isomers, it is, let's say, substantial, up to 0.3 electron. Here you see also dipole moment changes, which is also important because in this case we can change the work function of the electrode. If the dipole moment is close to 0, nothing happens. If it is substantial changes going from trans to cis under UV light illumination, then we can, let's say, change the work function of the electrode, which is again shown from this slide, which shows the HOMO-LUMO gap. The HOMO-LUMO gap for trans is very close to work function of gold electrode, and then it narrows substantially for cis isomers. And preliminary conclusions, which you can read, I mentioned already there during my talk. I only would like to thank the DFG for funding, and thank you very much for your kind attention.
Thank you.
All right, thank you, Olga. Very nice
Thank
talk.
you.
Very good computational work.
Thank you.
All right, if you have questions, make sure you post it in the chat window. We have our next talk, number 21 from Monish. Are you here? Monish? I don't think he's here. Monish? No? All right, so
let me share my screen.
Yes. Thank you.
Hello everyone, my topic today is about mode distributions and spectral characteristics for the chiral thin film resonators under B and S polarization, which is parallel and perpendicular polarization. First, let's talk about chiral slab resonator. As we can see here in the schematic, we have a chiral slab with a thickness D. To the left and to the right, we have a chiral material. We have the kappa factor here in the slab. we are coming with a one incident angle. Then we are calculating the reflected and transmitted waves in the slab, also the total amplitude and power transmitted and the total amplitude and power reflected out of the slab. And we are doing all that in the thin film limit, which is 10 to 100 nanometer. In the second slide, we are showing the first boundary of the slab. We have a one incident and two reflected and two transmitted waves. We have RCB and LCB for both, which is right circular polarization and left circular polarization for the reflection and the transmission. Here in equation number 1, we are showing the Snell's law, the standard Snell's law, but here we have a chirality included in the second medium, because the second medium is chiral, which is the slab. As we know, the chiral material is usually lossy material, so the relative permittivity in the second boundary, which is the slab here, will be complex. But here in these slides, we are showing the lossless case. The lossy graphs and results will be introduced in the full paper. Mathematical derivation, we have two reflection and two transmitted coefficients here. They are very complicated compared with the normal case. That's because of the chirality in the second boundary. We are showing some results for the coefficients, the reflection, the up two graphs for the reflection, and the bottom graphs for the transmission coefficients. As we can see here, we have some phenomena like Brewster angles, TIR, and so on, and these are shifted or controlled by the kappa factor. So we are changing here kappa from 0.6 to 2.1 to control these phenomena and see how that affects the transmitted waves. The same thing is for the second boundary of the slab. We have the transmission and reflection coefficient has been calculated. For the conclusion, since it's 3 minutes, we can't include all details here, so we're gonna talk about the thick slab resonator modes in details in the full paper. Also, the presence of dielectric losses in chiral slab and the thin film will be discussed in details, the parallel versus perpendicular polarization, and some ongoing work. Thank you for listening. Bye. Hello, everyone. My topic today is about mode distributions and spectral characteristics.
Thanks for the talk from Manish. Our next one is number 22. I do not see the uploaded video. Is Pamela here? I don't think so. Fine, can you also confirm that? I didn't see the video in the shared folder.
No, I didn't have.
Okay, how about 23?
Actually, I have the 26, the updated 26. I just have 26. Maybe you do not have 26, but I have the 26. That's the only thing I think we have difference.
Don't you see 24?
26. I just received 26, but I don't think I have 24.
You don't have 24?
24 is a PPT, yes.
Yes, I don't think we have the audio. So let us skip 22, 23, 24, 25. I just want to confirm any other authors for talk from 22 to 25. If not, we'll go to 26 from Kimberly. The topic is, let me see if the author is here. I don't think so. Kimberly, I do not see the author here. All right, so let's play the video for number 26, investigation of bioengineering composite bone scaffolds. All right, thank you, Huang.
Hi, the title of this talk is The Investigation of Bioengineering Composite Bone Scaffolds. My name is Kimberly Cook-Chenault, and I'm presenting on behalf of my lab as well as my graduate student Anila, Teresa Jeanette Rajesh Khanna, and my undergraduate student Zachary Yamer. About 500,000 bone grafting procedures are done in the U.S. per year. where bone scaffolds are an excellent alternative for substitution of missing pieces of bone due to bone injury or trauma, infection, or necrosis. Bones also demonstrate the piezoelectric effect, which aids in the stimulation of bone growth. A lot of materials such as natural and synthetic polymers, inorganics, as well as ceramic polymer composites have been considered as candidates for engineered bone scaffolds. This work focuses on ceramic polymer composites because they can be tailored to meet many of the challenges associated with the development and implementation of bone scaffolds, which typically are material compatibility, both in terms of mechanical and electrical properties, structural morphology, and the ability of the bone scaffold to facilitate adhesion, growth, and proliferation. So in this work, the research questions are: how do the processing techniques influence the mechanical and electrical properties, as well as what types of processes and practices can be used in order to achieve the ASTM standard that's used for testing bioengineered scaffolds. A conventional sintering mix and mold process was used in order to fabricate these samples, where what should be noted is that a two-step milling process, as well as a parametric study for optimization of the polarization process, was used in order to facilitate the fabrication of scaffolds that mimic the bone properties. The materials were characterized using the ASTM D695 standard compression test, where the samples were made with a 2-to-1 ratio, and the piezoelectric properties were also tested, where our results indicated that we were able to achieve ideal compressive strength that is compatible with that of bone, with a substantially smaller percentage of active piezoelectric materials in comparison to other works, and we were able to achieve fairly high piezoelectric strain coefficients that are comparable to those where there were substantially higher active piezoelectric materials. And this was due in part to the use of a two-step milling process, as well as optimization of the polarization process that is used in order to polarize the bone scaffold. This work is based on support from the National Science Foundation under Grant 1659-81-8. Hi, the title of this talk is The Investigation of Bioengineering Composite Bone Scaffold.
All right, I don't know what's going on, Buying, but it's very interesting.
Yeah, do we need to replay it?
Yeah, let's not replay it.
But I think maybe we should ask number 23.
24, I think. Is that number 23?
23.
That's right. Do you see the uploaded video? I didn't see it.
Yeah, I see it. I see it.
Okay, then you can play it.
It's in my mailbox. I don't know if Victor, do you want to present yourself, or do you want us to?
Yes, I would be grateful if you could play the video.
Okay.
Okay, sounds good.
Thanks a lot.
Wait a minute.
Plasmonic films are tremendously interesting materials that have practical applications for various optoelectronic technologies of the 21st century. They can be used to produce negative refractive index materials for cloaking, perfect absorbers, broadband circular polarizers, selective reflectors, and many, many more. However, there is a problem that achieving chirality, plasmonic chirality in solutions is achievable, is feasible. However, there is only a handful of methods that is able to produce thin films exhibiting chiral plasmonic properties, which are required for several applications. So in our work, we aim to combat this problem by combining recent progress in two fields, the field of liquid crystals and nanoparticles. So within the last 15 years, several chiral morphologies of liquid crystals has been discovered. Small organic molecules on freezing assemble into, for example, helical nanofilaments with dimensions comparable to nanoparticles, and this makes them especially attractive for producing chiral plasmonic composites. We summarized the recent progress in one of our review papers. But then, if chemically compatible nanoparticles are added to the organic matrix, these nanoparticles tend to be well dispersed in the isotropic phase at elevated temperature. However, on freezing, they locate selectively on the edges of helices, producing chiral plasmonic assemblies. In one of our recent papers, we have shown how to use this strategy to produce chiral plasmonic films that exhibit chiral response on the microscale. So small domains of one-of-the-handedness were produced, and we confirmed that they actually interact with circularly polarized light in a different way. However, in our recent work, we aimed to develop the ability to produce microscopic bulk scale systems which exhibit either right or left-handed properties. And we successfully achieved that by doping the chiral plasmonic systems in the isotropic phase with a small amount of chiral low molecular weight compounds. This way, we achieved the ability to control handedness, chiral response of the materials at the bulk scale, but also we have shown that there are several types of nanoparticles that are compatible to our systems, and thus we can control the spectral range. Chiral plasmonic films are tremendously
All right, that's it, right? Is it half done? Fine.
Yeah, it have done.
Okay. All right. Thank you for the particle assembly work. Between
Thanks, Claude.
yeah, thanks. Hua-Ying, do you have anything about the 24, 25?
24. For 24, we have a presentation version. The PPT, let me see. I think.
I don't think we have audio. You can check it. It's just
no, I don't think I see any audios.
Yeah. Okay, lesson replay 26, the last one.
Yeah.
Okay, thanks.
Hi, the title of this talk is The Investigation of Bioengineering Composite Bone Scaffolds. My name is Kimberly Cookchinall, and I'm presenting on behalf of my lab as well as my graduate student Anila, Teresa, Jeanette, Rajesh Khanna, and my undergraduate student Zachary Yamer. About 500,000 bone grafting procedures are done in the U.S. per year, where bone scaffolds are an excellent alternative for substitution of missing pieces of bone due to bone injury or trauma, infection, or necrosis. Bones also demonstrate the piezoelectric effect, which aids in the stimulation of bone growth. A lot of materials such as natural and synthetic polymers, inorganics, as well as ceramic polymer composites have been considered as candidates for engineered bone scaffolds. This work focuses on ceramic polymer composites because they can be tailored to meet many of the challenges associated with the development and implementation of bone scaffolds, which typically are material compatibility, both in terms of mechanical and electrical properties, structural morphology, and the ability of the bone scaffold to facilitate adhesion, growth, and proliferation. So in this work, the research questions are: how do the processing techniques influence the mechanical and electrical properties, as well as what types of processes and practices can be used in order to achieve the ASTM standard that's used for testing bioengineered scaffolds. A conventional sintering mix and mold process was used in order to fabricate these samples, where what should be noted is that a two-step milling process, as well as a parametric study for optimization of the polarization process, was used in order to facilitate the fabrication of scaffolds that mimic the bone properties. The materials were characterized using the ASTM D695 standard compression test, where the samples were made with a 2-to-1 ratio, and the piezoelectric properties were also tested, where our results indicated that we were able to achieve ideal compressive strength that is compatible with that of bone, with a substantially smaller percentage of active piezoelectric materials in comparison to other works, and we were able to achieve fairly high piezoelectric strain coefficients that are comparable to those where there were substantially higher active piezoelectric materials. And this was due in part to the use of a two-step milling process, as well as optimization of the polarization process that is used in order to polarize the bone scaffold. This work is based on support from the National Science Foundation under Grant 1659-81-8. Hi.
All right, I think that's it. We have missed a few talks, 5 or 6, but I think that's it. We don't have number 7. Is that correct, Faying?
Yes, I think that's all we have.
Okay, thank you again. We still have a few attendees here. I think we are ahead of the schedule, but I hope you can enjoy the rest of the seminar for other excellent talks. Thank you very much, and you can leave the webinar, I guess. That's it, right? So we are all leave.
Yeah, wait a minute, Professor Song. I think, could you recommend 2 or 3?
Yeah, I received the email, and I'm going to reply to Imran Shakir.
Yeah, Professor Shakir.
I'll email the nominations, so don't worry about it.
Yeah, great.
Okay, that's it. Thank you.
Thank you, Professor Song. Yeah, bye.